This is video 5 for the atoms and heat unit. This one we're going to talk about efficiency. Now, it turns out that there's a very fundamental theorem that can limit how much heat can be turned into useful energy, which is kinetic energy. So if you think about a car's engine, there's tiny explosions going on inside the cylinders as the gasoline burns. And what we're trying to do is we're trying to turn that heat from the burning gasoline into the kinetic energy of the car. Now, this fundamental theorem was one of the greatest achievements in the theory of heat. And, we have to realize first that heat can be extracted to be turned into kinetic energy, but only when it flows from a hot region to a cold region. So for a car, the hot region is inside the cylinder. The cold region is the atmosphere. It's outside of the tailpipe. So, for the car motor, when the gasoline burns, we talked a little bit about how when something explosive is burnt, that it's turned into heat energy, which then warms up the air, and that gas expands by quite a lot. For dynamite, it was a factor of 167. So we see the same thing here. When the gasoline burns, it's hotter than surrounding air. That allows it to expand and push against the piston. So there's some sort of pressure. It rapidly increases the pressure inside of the cylinder, and then that exerts forces on all parts of the cylinder, and there's one part, the piston, which is movable. So that force pushes down on the piston, pushing it down. Now, what's important to realize, though, is if the surrounding air was just as hot as that burnt gasoline, the piston would not move. The pressures would all be the same. So, for a car, which is basically a heat engine, they depend on a temperature difference. There has to be some place for that heat energy to flow, because heat is energy flowing from a hot region to a cold region. Now this leads us into a formula called efficiency. So basically the efficiency, and actually we kind of use a Greek letter sigma for efficiency. It equals the number 1 minus the cold temperature divided by the hot temperature. We can use this formula then to calculate the efficiency of a heat engine. Gasoline engines are about 20% efficient. So that means 80% of that heat energy is lost forever. So you need to have a temperature difference to extract useful energy from heat. Um, you cannot extract heat from a single object just to turn it into useful energy unless there's something colder that you can use. And this is something so important that it's been given a name, the second law of thermodynamics. So, looking at this then, efficiency tells us how much of that energy is being able to be turned into useful energy, being able to turn it into kinetic energy. And notice that efficiency rises when we have a greater difference between the cold part and the hot part. And again, that's something that's very important to realize as well. Okay, refrigerators and heat pumps. I'm sure everyone has a refrigerator. A lot of people may have a heat pump. I have a heat pump in my home that I use to help warm and cool it. So the heat engine requires a temperature difference, something hot and something cold, such as the car. It is possible to reverse this process. In other words, to take kinetic energy or mechanical motion and use it to create a temperature difference. This is what we call a refrigerator or a heat pump. So the way they work is they use a mechanical force to reduce the pressure in a chamber, and then that will, obeying the gas law, we can then see that the temperature would have to drop as a consequence. This mechanical force is usually done through a piston. We use a tiny electric motor attached to a piston that will reduce the pressure in some sort of chamber. Now, remember, the ideal gas law says that pressure equals a constant multiplied by the absolute temperature. So, if we think about this then, as the pressure drops, the temperature must drop as well. And that is how we can make a refrigerator. By reducing the pressure in a chamber, we lower its temperature, and then we can run some tubing through there with special fluids that are very sensitive to temperature changes, and then we can go from there. I've got a little picture here showing a basic schematic. That mechanical force reducing pressure, we call that a compressor. So you can see the compressor in that. By running the device forward and backwards, we can either heat or cool something. Okay, so this next thing I want to do is just take a quick review of some things. So first off, let's review the zeroth law, and that's basically objects in contact tend to reach the same temperature. And that's basically how thermometers can work. The first law. We haven't spent a lot of time with the first law in this unit, but we have in the last one, believe it or not. The first law is conservation of energy. Energy is conserved. The second law we just kind of mentioned. So the second one, you cannot extract heat without a temperature difference. So the second law is how your car works. By extract, I mean turning heat into kinetic energy. The third law, we haven't really talked about it too much, but it's pretty easy. That's basically saying that nothing can reach absolute zero. You cannot force every single atom to stop moving. So, there it is, the 4 laws of thermodynamics. Last but not least, let's just take a quick review of the way that heat flows. First off, we have conduction. So this is where energy flows by contact. Convection, this is energy carried by a moving material. So as you can see, convection would only work with liquids and gases. So think about convection currents, hot air rises, things like that. And finally, radiation, this is energy moving through empty space. And this is actually through infrared radiation or infrared light. We'll talk about infrared in greater detail later. Of these 3 ways for heat to flow, that arrow points in towards the least efficient means. So the most efficient way to get heat to flow is through conduction. The least efficient way to get heat to flow is through radiation. And that concludes this entire unit.